Now we are going to enter in another important topic is a potential flow, and what are the types of potential flow and how we are going to correlate with that in the velocity and the string function. Here we are going to see the connections between those. So we have a couple of the types of potential flow. Okay, uniform flow, source flow, string flow, vortex flow, doublet flow, and the random combinations of it. Now these are the basic types. Okay, these are the basic types of the potential flow. Now here what we are going to do is that first we are going to see the nature of these flows. Okay, nature in the flow means like whether it is incompressible, whether it is a rotational, and after finding that we are going to find out the the velocity potential and the string function, and what is their stagnation points, if they have to form the stagnation point, what kind of velocity is forming, whether it is a radial velocity or it is a presence of tangential velocity. Okay, so and what are the possible significance, what will be the coefficient of pressure. So all those factors we are going to see both in numerically as well as in the significance factor. Now this is one of the very important topic. Okay, very important topic in terms of problems and also based on the concept point of view. Now we will move to the next. First, one by one we will see, starting with a uniform flow. Okay, uniform flow. Now when I talk about uniform flow, that means it has to be flow. Here in this figure it shows that the flow is horizontally moving from one point to another point. The flow is moving from one point to another point, considering the free stream velocity is v infinity. Free stream velocity is v infinity. Okay. Now let's understand the basic definition of the uniform flow. Now this what it matters. Okay, this what it matters. Here the uniform flow signifies that the flow is incompressible. Now when I say the flow is incompressible, that means I can also write del dot v equals to 0. I can also signify del dot v is also equals to 0. And also not only it is incompressible, but it is also a rotational. Okay. Now when I have to signify the rotational in a mathematical form, we can also write del cross v. Okay, or we can say del curl into v or del gradient into v. So this is one of the both the numerical one as well as the physical significance. The uniform flow is always incompressible and irrotational. Okay. Now this what happens. So what, as I said, first we are going to find out whether the flow is radial. So when I consider v suffix r, it represents the flow, because whenever the flow is moving it has to divide in two components, because here we are going to study the 2D flow. Okay, by default here we are studying the 2D flow. So we are going to see that whether this flow, okay, when this flow is dividing two components, it will split up in two different components. One is a VR and is v theta. VR means a radial velocity, theta means a tangential velocity. Radial consists of radial, theta consists of the tangential velocity. Okay. Now once we find out this radial and tangential, we can find out the resultant velocity. How? Resultant velocity is always the same, by VR square plus v theta square. Now using this relation we can again find out the resultant velocity. Now after finding the resultant velocity, how we can obtain the stream function and the velocity function. Okay. Now again let me give you a basic recap between the stream function and the velocity function. Now when we talk about the stream function, that is phi, okay, psi, right, it is a 2D flow. It is a 2D flow, and when we consider this phi, that is our velocity function, it is a 3D flow. Now in the stream function, when we discuss, the flow can either be rotational, this stream function can either be rotational or derotational. Okay, it can be rotational or irrotational, but here in this velocity potential, it is fixed that if it satisfies, it has to be irrotational, steady and incompressible. And here we can do in two different forms. One is a polar and second one is a by means of Cartesian coordinates. Okay. Two coordinates. Now here in your exam point of view, they can give either of the coordinates. One can be the Cartesian and second one can be the polar. So I request you have to prepare both carefully. Okay. So previously we have also seen that when we are discussing about this stream function for stream function and velocity potential, when we want to find the velocity, that is u and v, what was the formula? That we used to write phi equals to, if I have to write in 2D form, we can write u equals to minus dou phi by dou x and v equals to minus dou phi by dou y. This is u and v. So similarly, if I want to write down the stream function, we can also write likewise minus dou psi by dou y and dou psi by dou x. I can write this. Now this is the form of Cartesian coordinates when they have given the x and y, and you can use this formula. But here when we go for a uniform flow, you have to always be careful with the coordinates, what coordinates they are asking, and in that form the coordinates, how you can convert that. So this is the equation. It can be also written in this way. Okay. So here you have to also remember this formula. So when we note down the value for in terms of polar coordinates, we write in terms of Vr and V theta. Okay. So when we want to write down for an velocity potential, Vr equals to dou phi by dou r and theta equals to 1 by r dou phi by dou theta. Okay. This is in terms of velocity potential. Now what will you write if you have to write for a stream function? You have to write 1 by r dou psi by dou theta, and in terms of this will become minus of dou psi by dou r, dou psi by dou r. So you have to remember this expression. So here when we are going for this potential flow, both the Cartesian and as well as the polar coordinates we have to remember, polar form. Okay. So you have to remember this relation of this radial and the tangential one. Okay. I hope it's clear till here. Is it clear? You can drop in the chat box.
Yes, ma'am.
Okay.
It is clear for me.
Alright. Now for an example, how to obtain this phi and mu. Okay, how to obtain this phi and mu. Now when this velocity is moving, there is a small derivation here. We are not focusing on the derivation, but yes, you have to remember the final expression over here. Now as you know, this phi and mu value is given. Now this is the values which you can see. These are for the polar values. Now if we have to write in kind of Cartesian coordinate, what will be the formula? Phi equals to v infinity into y, and for the velocity potential it will be v infinity into x. V infinity into x. That means from here you can easily obtain that r cos theta equals to x. That means cos theta means x by r. Okay. Similarly, here we have that v infinity r sin theta, and which can be also be written as v infinity y. Okay. So that means it can also write as r sin theta equals to y. That means sin theta equals to y by r. Suppose they have given you in the form of Cartesian coordinates and they want to find the theta value or something, so you can use this formula. Now how to find r? So always remember the r represents like x square plus y square. So r equals to root over x square plus y square. Now if the x value and the y value is given, you can find the r. So, and second important thing, if there is some kind of value only theta, okay, there is no sin theta or kind of cos theta, if only the factor theta, that means you have to convert that in terms of radian. Convert that in terms of radian. Now from this equation, from this uniform flow, you can obtain these are the important parameters. That means both in the polar and the Cartesian form. Okay, that is phi means that is v infinity x, and psi is v infinity, that is a twisting velocity into y. And okay. Now next very important is what it signifies. Another important thing, the velocity potential for uniform flow can be obtained, that it can be also written as like this. The velocity potential.
Excuse me, ma'am.
Yes.
How to just convert this theta into radian, ma'am? I forgot.
Okay. So whatever the degree you have into pi by 180 degree. Okay. So whatever the value will have, right? So that one into pi by 180. So we will do in the problem. I will let you know about that.
Okay, ma'am.
So a very important key point, that if there are something like how this velocity potential and uniform flow are correlated, so you just remember this important statement. Okay, so the velocity potential for a uniform flow can be obtained that del phi equals to v. Okay, this is an important statement. Now next important statement, that they can also relate you in terms of circulation. Okay, so circulation, how you can relate that? Again, circulation you can relate with this. This is another terms of gamma. Okay, capital gamma. Circulation can be denoted by the capital gamma. Now circulation around any closed curve in an uniform flow is zero. Just remember this statement. This is a very important statement. Okay. Now foreign, this is for the circular, that means there is no vorticity around this uniform flow. So circulation is zero means there is no vorticity, and it also represents the flow is irrotational. Okay. So the circulation will be zero. Now next important key point is A uniform flow is irrotational, that is del curl into V equal to 0, and whether it is a particular point or it is in the infinite field of flow, so it is represented, it flow happens everywhere, and wherever the uniform flow it represents, the circulation will also be 0, which leads that circulation is 0. Okay. Circulation 0 represents that flow is also irrotational. These are the key points. They might ask a one question based on these factors. Now, as I said, we have the velocity function, that is Vr and V theta. Now, how to obtain Vr and V theta? Once you have obtained this phi and psi value, the Vr value is known. As I've said, what is the Vr? If you want to find the string function, mostly here we deals with string function because it is a 2D function. So here all we deals with 2D. So in the textbook or other author also represent in terms of string function. So you need to remember the formula. What is Vr? Vr is 1 by r dou psi by dou theta, and V theta equals to minus dou psi by dou r. Okay, you remember this formula, you know the phi value, from this statement. Okay, since it is a polar coordinates, you have to use this formula. So when you differentiate with respect to theta and r, you will get the Vr. Now to find out the stagnation point, you have to always set this Vr equal to 0 to find out the stagnation point, because the velocity either it can be a radial or the tangential, the velocity has to bring to an rest. So to find out the stagnation point, we have to use this formula and equate to 0. Now this is about the uniform flow, and similar way we will also move to the next flow, is a source flow. Now let's see what this source flow represents. Okay. Now from the word you can understand, that is the flow is starting or the emerging from some point and expelling or emerging outwards from some of the center point. So again they have stated that the source flow is a two-dimensional flow, incompressible flow. Okay, they have stated it is a two-dimensional incompressible flow where all the streamlines are straight line emerging out from the center point. But here they have not said that whether the flow is irrotational or not. Here they have not stated that whether the flow is irrotational or not. Okay. And one more thing here, one more important point is, in uniform flow the velocity always remains constant. Here the velocity always remains constant because all the fluid particles moving with an same velocity. Okay, this is one of the, you can consider as an assumption, the velocity, that is a free stream velocity, remains constant. Okay, now source flow, as I've said, that any flow that is coming out from one point, okay, and radially moving in all the directions at an uniform rate. That is also one of the important term you can consider as an uniform rate. Now when in the source it is coming, we consider one of the very important consideration, that is the strength of the source. Okay, now what is mean by the strength of the source means, which is the, you can say, the uniform rate, that is at what uniform rate it is coming. The strength of the source, that is denoted by, again, kind of lambda, capital lambda, okay, which is nothing but the volume flow rate per unit depth, okay. So you can also represent that as an uniform rate or the strength of the source, okay, strength of the source. Now here we have some additional component is the strength of the source. Now here we have a formula like this, which is strength of the source can be written as VR to pi r. As you can say, I have stated the velocity component has been classified in two forms. One is the radial and the tangential directions, and here the tangential direction is 0. So we can equate that the strength of the source can be equal to the radial velocity into 2 pi r. R is at what diameter that it is flow is expelling. Now from this we can also write, that is VR equals to lambda 2 pi r. This is also another important expression. Now if the strength of the source is constant and 2 pi is obviously constant, then we can state that the velocity along the streamline is inversely proportional with the distance from the point O. Okay, and that kind of flow, when they are inversely proportional, that flow is also known as a source flow. Okay, now this is the formula. As I've said, here you can see the formula, and since the source, the strength and divided by 2 pi is a constant, so I can write in this way, VR equals to constant C by R. This is a constant, and where the constant is nothing but lambda by 2 pi, So I can, in that case, I can state that the velocity means, here we have only one velocity, that is a radial velocity. Tangential velocity is 0. We don't have that. So we can state that it is inversely proportional with the distance. Now these are the key points I am discussing, because there can be kind of question, either theoretically they can ask or state, or they can use some of the numerical questions. Okay. Now what it represents when I say that VR is along each of the streamline varies inversely with the distance. Now can I say that if the distance, that is R, okay, if the R increases, then what will happen with the radial velocity? Obviously it will be less. Now if the R is too large, now gradually the R value is increasing, then finally VR will lead to also be 0. Okay, the VR will also lead to be 0, right? It will gradually come down in such a way that it has to be, VR will also has to be lead to be 0, if only the R is large enough. So we can also state in this way. Now if the R is less, then we can represent the VR will increase, that is a radial velocity component will increase. Now moving to that, as I said, this equation. Now again we have to see how this flow is comparatively or connected with an incompressible flow and the irrotational flow. Now this is another very key important point to remember. So in uniform flow, what we have seen, the flow is incompressible and irrotational at everywhere, and wherever the flow is uniform, the circulation will be zero. Now here we are talking about source flow, and here we see the very important term that or the expression that they have declared, that the flow is incompressible flow only it is possible at every point except at the origin. That means when it is starting or emerging out from that initial point, except that everywhere the flow will be your incompressible. Okay, that means the flow will be incompressible, and that what the point is called as a where the flow will become that means at the origin. That means the origin, it won't satisfy that del dot V is not equal to 0. Okay, and that says that in the origin point, the del dot V is infinite. Del dot V is infinite, and where the del dot V is infinite, that particular point is called as a singular point. Okay, just remember the term as a singular point. These are the mathematical terms. Okay, where some del dot V, when it becomes equal to 0, okay, 0, they define as a singular point. So at the origin we have the singular point. That means that it doesn't satisfy the del dot V is equal to 0, but in fact it is just infinite. But apart from that origin, that when it is radially expelling out or emerging out from the source, it will be del dot V equal to 0. Now let's look, this is for the incompressible flow. Now what happens that whether the flow is rotational everywhere, or again it is just focused in some of the origin or all the points. Now here they have said this, in the source flow, the flow is irrotational at every point. The source flow explains that it is irrotational at every point, that is irrespective of the origin and when it is expelling out. Now these are the key terms that we mostly avoid during the exam. So they can also ask some kind of assertive and the reason question. So you can also expect some kind of assertive and the reason question. Like they can ask you the first statement, like they can give you the first statement from here to here. Now next statement they can explain, they can say because the flow at the origin is infinite and also consider a singular point. And they will ask you whether the statement or the assertive A and the reason R is true, or which one is the true, whether it is the right explanation with the assertive or the reason or not. Okay, or the statement which they are explaining is true or false. So such kind of statement can also come out from that. Now here what you have to remember, another important is the expression. Okay, where this is the strength, source strength, or the strength of the source. Now this strength of the source becomes positive. If it is a positive value, that means it represents, it is a source. That means from the point O, from this point O, it is emerging outwards. And when we say sink flow, that means from the outward flows, it is emerging into a single point O. It is coming into the point or towards the point O. So when we say the flow is coming or emerging and connecting into the towards the point O, the center point O, that means the flow is sink flow. Okay, and in that case what will happen, the strength of the sink, okay, when we consider the same formula, that is VR will becomes minus of lambda 2 pi r. Okay. That time we have to represent the minus sign. That minus sign of the strength represents it is a sink flow. Okay. Next important statement, it says that Now we will look into that, what is the phi and what is the psi. Now phi and psi, there is a big kind of derivation are there. Okay, so from it has been obtained from the derivation. Alright, so again I am telling, it is not an important, but you have to remember the final expression for the phi and psi. Now always remember, these are the constant terms. Okay, now these are the constant terms, and from here what you have to obtain is, you have to obtain VR and V theta. So already for the source flow, V theta is already 0, VR exists. And what is VR? It is lambda by 2 pi r. Lambda by 2 pi r. Okay. And it can be also stated in this way: VR equals to 1 by dou psi by dou theta, and theta equals to minus dou psi by dou theta. Okay. Now these final expressions are very important. Now if in the problem they are asking in terms of theta, now here what you have to convert? You have to convert this theta value in terms of radian. You have to convert the theta term in terms of radian. Let's look into that significance point of view. Now as I've said, okay, you know this is a function they have given in terms of stream function. This is the function or the expression they have shown by means of stream function. Theta represents at what angle the flow, each and every flow is emerging outwards. Okay. Now, and this factor is constant. Okay. Now let's see how the stream function will change when there is a different angle, or I can say in this way also, when each stream function moving or expelling out or emerging out, what will be the stream function? Now let's look into first one, when theta is equal to 0. When theta is equal to 0, okay, then the stream function will also be 0. Okay, so also be 0. Now let's look into it when there are in different angle of incidence. Okay, now if we have 45 degree, okay, now 45 degree can be written as 45 into pi by 180. Now when you do 45 into pi by 180, you get cancel off, you get pi by 4 in terms of radian. Now you know the formula, that is a lambda by 2 pi into pi by 4. When you simplify, you get this in terms of units. One more thing, the lambda is a strength or source, and which represents with the unit the meter square per second. Okay, the unit of the strength of the source is meter square per second. Okay, so please ensure that. Similarly, if it is 90 degree, so what you're going to find? What you are going to find in terms of radian. Okay, so 90 into pi by 180. So always, if there is without any sine, without any cos, or without any tan, if any theta is there, then ensure that whenever you are solving the problem, you have to use or convert in terms of radian. You have to convert in terms of radian. Okay. So you get pi by 2. Now you know the formula, basic formula, right? In terms of theta, you are going to just substitute the value, you are going to get the unit. Similarly for that. Okay. Similarly, so you will know what is the stream function at different angle of incidence when it is expelling out from the origin. Okay. And these are the lines which you can see is a streamline. Okay, these are the streamline. So remember the figure also. Remember the figure, whether it is a velocity line or the streamline, what is the nature of each line. Right now, how I can say this is a streamline? Because when I'm using this formula here, I can represent in this way. But here in this kind of velocity potential, we have some factor called r. So when I have to use this formula r, that means always I will get something like concentric circle. Okay, in this case I will represent the flow in terms of concentric circle. Okay, that means the velocity, this will be the, if it shows some kind of concentric circle for an source flow, that means it has to be the velocity potential function. If it is radially like this, okay, that has to be the stream function. Okay. So wherever because in this formula that velocity potential in terms of r, so that means the flow will represent in terms of concentric circle. Okay. Now is it clear to all of you? The schematic or the source and the sink, is that clear?
Excuse me, ma'am.
Yes.
Ma'am, can you just repeat the last point, ma'am, about the stream function velocity, like a potential function?
Okay. See the function. Now what is the function? Let me remove everything. Now what is the function? Pi equals to lambda by 2 pi ln r, okay, or ln r. So that means it is your velocity potential is a function of r. That means this part is constant, this is not gonna make any changes. Now if I have to draw the, what is the nature of when how this r, that is r is a radial distance, okay, radial distance from the source. So if I have to find out that, that means it will be in the nature of the circle, or you can see in the source diagram a dotted line or the circle is drawn, right? Now if any figure is given to identify that which flow will be, the right option among all, okay. So if it is a source flow, they are asking the velocity potential has to be, if it has to draw right at each interval of r, that is a radial distance, each interval of the radial distance, that means the nature of the velocity potential has to be the concentric circle. That means there will be a same point, and from the same point we will be having the circle after circle, the changing in the radial distance. Okay, if this kind of figure is given, that means it will represent the velocity potential for the source flow. Velocity potential for the source flow, because that represents the radius or the radial distance in terms of phi. Phi means velocity potential. Now if you see in this function, that is a stream function, in terms of some theta, that means some angle, that means that it represents the stream function. When we are giving some kind of figure, something like this, okay, something like that, okay, we have the same origin and expelling out, okay, expelling out, that means the angle from here to here is theta, right? So here to here is another theta, right? It is starting from here then gradually going. Now when we represent in terms of theta, that means that particular function will be the stream function. Now here the stream function for a source flow will be this radial graphical representation. Is it clear?
Sure, ma'am, it's clear.
Okay. So these are the things you need to identify for your competitive exam. Okay. So you know the figure, but you don't know what is the velocity function and why we are choosing that particular one, and what to find out for the stream function. Okay. So this is a very important or the key points. Okay. Okay. Now moving to that doublet flow. Okay. Now doublet flow, as you can say, it is the when we are combining the source and sink. Okay, when we are compiling the source and sink. Now when we are compiling the source and sink, that time we will not consider the source as we have considered, that is a that is suppose lambda is positive, that is the strength of the source is positive, and the sink we consider negative. Now here when they compile together, the compiling of two will give a different kind of strength of the flow. Okay, so that here represents in terms of K. Now why we have a different kind of significant value? To identify each will represent different strength. Now here that means it says that here we are not going to find for the source and sink separately, but it will create a different another new different kind of strength. Okay, now unit remains same for the strength for or whatever the strength I consider, whether for a uniform flow we don't have any strength. For the source flow, doublet flow, even we will upcoming we will see the vortex flow, we will see all the different kind of strength. Okay, and all the unit are same, that is a meter square per second. Now there is another unit for the meter square per second, that is the kinematic viscosity. Kinematic viscosity have the same unit. Now what happens here in this doublet flow? Okay, now doublet flow, here as we have seen that what is the nature of the radial flow and the tangential flow. But here in case of doublet flow, both the radial flow and the tangential flow exist. Both the flow exist. Okay, both the flow exist in case of doublet flow. Okay, and please do note down the formula. If I want to write, VR equals to K by 2 pi cos theta by r square, and V theta equals to minus K by 2 pi sin theta by r square. So what is VR? VR means 1 by r dou psi by dou theta, and here means minus dou psi by dou r. Okay. So you know the psi value. So when you use this partially differentiate with respect to theta, you will get this expression. Okay, so here both the radial and the tangential flow exist, and if they ask to find out the stagnation point, so what you have to do, you have to equate this value to 0. And always remember, if there is any velocity or something, you cannot equate them to 0, because velocity or the free spin velocity never be 0. So you have to see what are the possible factors can be 0. If there is something called a cos theta values or something, then it can be possibly taken or considered as 0. Okay, so if there is any component like velocity or something, you cannot equate them to 0. Okay. This is all about the doublet flow. Now another important fact, that what is the equation of a doublet flow in terms of Cartesian coordinates. Now there can be a possible kind of problems they can ask. So this is the formula. Previously we have seen the psi equals to minus K by 2 pi sin theta by r. Okay, this is for the polar coordinates. Okay, and this is for the Cartesian coordinates. Now if they have given this x and y for any problematic statements or something, so you have to use this formula to find out the, already we have discussed the sin theta value and the r value. Okay, sin theta and r I have already discussed. So you have to use this expression to find out the result. So these are the formulas will be useful in a numerical point of view. Okay, next is we have the vortex flow. Okay, vortex flow, what it represents, again it is, we are discussing about the 2D flow. 2D flow. Now a flow where all the streamlines are concentric circle about a given point. Okay, about a given point. Now what happens here? Sorry. Okay. Now that means from one point each circular formation occurs at some point, just like an if you drop a stone in a water or in a stagnant point, right, you can see the vortex formation. Just like that, that is a great example that I can give for an vortex flow. Okay. Now here let's see how this formation represent in terms of radial and the tangential flow. Now here the radial flow, if I consider VR, if it is a radial velocity is 0, but here the tangential flow exists, and that is nothing but the constant by the r. Now again, what is the constant over here? Here we are again taking the different kind of constant, that is the strength. Here the strength are represented by the gamma by 2 pi. Gamma by 2 pi. Here the strength we are representing in a different notations. Okay, that is a gamma by 2 pi. So I request all of you are noting down the formula, right? So again it states that,
Ma'am, the strength is represented by what, ma'am? What denotation of strength?
this is the gamma, capital gamma. Okay, just like a circulation.
Okay.
That means here we can state that there will be existence of circulation. We cannot say that circulation will be 0 over here. So just like we have seen in an uniform flow, there won't be any circulation, right? But here there will be a circulation. Okay, there will be the existence of circulation. Now if this constant term, that is the constant term represent, that is a gamma by 2 pi. Gamma by 2 pi is a constant. Now if it is constant, again how it is interconnecting with each other? Here the tangential flow, if the tangential flow increases, what will happen with the radial distance? Radial distance will again decrease. Okay? This is the one of the significant point you can obtain from here. Here we are talking about the tangential distance, but not the radial one. Not the radial one. Now here one more thing you can find. One more kind of questions they can ask. Now they can give you the statement like, there are two vortex flow. Okay, two vortex flows. Let's consider a point A. Let's consider a point A and point B. Okay, point A and point B. Both the point A and B, it is creating a vortex flow. Okay, it is having some kind of vortex flow. Okay. Now one radius is something maybe 1 meter. Another one radius is forming 2 meter. Okay. Now from here they might give the velocity also, velocity for the one of the parameters. Okay, you can give the velocity for tangential, obviously tangential velocity has to be given. Okay, now they might ask you what will be the tangential velocity for the other one. So how you can find? You have to consider the strength, okay, or the constant term is constant for both. Using that you can find out the unknown factor. You can find out the unknown factor. Now in this, if they give the pressure, that is for the A point, PA point is maybe of 2 Newton per meter square. 2 Newton per meter square, and you have to find for the V1. Now this kind of question can also ask, now how will you find out the pressure for the V? What will be the formula will you use to find out for the pressure for the V vortex? What formula will you use?
Ma'am, can you explain about that velocity again, ma'am? V theta is given for only one term, is it?
Yes, V theta is given from 1, that is for the A component it is given, the A vortex, okay, it is given, but V1 they have not given. You have to find. How will you find? We can use this V theta, suppose A equals to, I can say the constant term divided by the radial of A. Can I write? Now constant is,
Yes.
I can say the constant term is that fixed, right? So can I say V theta of A by V theta of B equals to R of B by R of A. From that our requirement is V theta of B. I know the V theta of A. V is known, that is 2 meter. VA is known, that is 1 meter. I can find out the V theta of B, right? I can obtain that value.
Okay, ma'am. Got it.
Okay. Now in this case, in addition, they have given the pressure also. Now pressure is also given for the PA, and how to find for the PB at the point B, what is the pressure obtained. So again here, exactly. So here you have to use the principle. What is the formula? P by rho plus V square by 2. Okay, will be, if this for A, then B, you have to use this formula. You know all the parameters, and you can find out the unknown one. Now density, it will depend again if there is a different density they have said. So if they are same, then you have to ensure that sometimes they may not give you the density. If they use air, then you have to use 1.225. If they are giving water, then you have to use 1000 kg per meter cube. So accordingly, based on the statement, you have to put the density value. So this kind of questions you can also expect from this particular topic. Okay. All right. So yes, another very important statement, that how this vortex flow are physically changes in terms of incompressible flow and for the irrotational flow. Okay, now let's see the statement here in this vortex flow. Okay, it is possible, the flow can be possible in compressible flow at every point, that means, that is del dot V has to be 0 at each and every, starting from the O point and as it radially moves outwards. Now let's look into the consideration of the irrotational flow and when it is possible. It is only, we know the irrotational means del cross or the curl. We can also cross, we can say as a curl. Okay, or del cross V equal to 0 at every point except at the origin, Okay, this is a very important key term. Now can you tell me that which is the reverse impact of this statement, where we have the reverse thing, where the compressible flow, that is compressible flow will be everywhere except origin. What was the name of the flow? Except at the origin. What was the name of the flow? You can answer.
Source flow.
It is a source flow. Exactly.
Source.
Very good. Exactly. So that is a source flow. And what happened in the source flow? where all the flow is rotational at every point. But here in the vortex condition, it is just a reverse thing. Here incompressible flow is at every point, but the irrotational flow is at every point except at the origin. Okay, except at the origin. Now, as I've said, here there will be existence of the tangential flow, okay, and the rotational flow, radial flow will be 0. It is just again the reverse effect of the source flow. Okay, and remember this formula, that is V theta equals to minus of R. Okay, V theta is minus of R. Let's look into that. What is the phi and psi? Okay, phi is a velocity potential, and psi is a stream function. Now you have to again remember this equation. Now if I have to draw again for the velocity potential and for the stream function, now what I can say that if any figure represents the kind of like this, okay, that means it will be the velocity potential, where we can represent the flow in terms of theta, and here you can see the stream function represent with of R. That means the flow, when you want to represent the stream function flow, it has to represent in this form. Okay, in this form. Okay. Now to obtain again for the VR and V theta value, you have to set to 0. Stagnation point has to be 0 to obtain the stagnation point. Now again, what is a VR? I am telling you repeatedly so that this formula will move to your head directly. Okay. So V theta equals to minus dou phi by dou R. Okay. All right. As I've said, this velocity potential has to be in this radial one, because we have the theta in terms of theta. Now similar way, how you can find with a different kind of theta, right? Put that in the value. Theta if has to be 45 degree, right? It has to be 45 degree. Then substitute that over here. Phi value is minus by 2 pi into 45 into pi by 180. Simplify that, you will get the phi value for that particular point. Okay. Obviously it is a negative value will come out. Okay. So similarly, if any kind of questions comes like that, what will be the value phi functions for this at angle, you can easily find out that. Okay, you can easily find out. Now what will be the unit if you substitute over here? Again the unit will be meter square per second. Okay, the unit will be meter square per second. Alright, now here becomes the combination of the flows. So you have to remember the formulas of that along all the directions. So here source flow, the tangential flow is 0. In vortex flow, the radial velocity will be 0. In doublet, both the existence of the tangential, the radial and the tangential will exist. Okay. Now here I used to use some of the shortcuts to remember this formula. Okay. Now this is very easy to remember for the velocity. It is for source the tangential will be 0, and for the vortex radial will be 0. Okay, and the formula is known, the constant by R. That is a fundamental facts. These are the constant and these are the constants. These are the constants. Okay. So both are inversely proportional with the earth. Either it's a radial or it's a tangential one. Now how to remember the phi function and psi function? Once you remember this phi and the psi function, you can obtain the VR and V theta value. Okay, VR and V theta value or vice versa. From here also you can find out this phi and psi value. Now again remember we have the constant terms ahead. We have the constant term ahead. That is, this is a constant term. Okay, constant term. Now remember this, when you write ln, remember source and vortex, because source and vortex are interconnected with each other. Source and vortex where you can get confused, both having in terms of ln r and theta. So I should remember like this. I remember the first comes source, then we studied vortex. Okay, SV, then ln r theta, then theta ln r. Okay, now here when I am doing this, here I just remember the minus sign. Okay, here I just remember the minus sign. So I used to remember this particular thing. I just used to remember this particular thing. Ln r, here theta, and here minus theta ln r. So I know what are the constant terms for the vortex and the source, but only the main confusing part is this factors. So I should remember this way.